Okay.
Okay. You'd like to introduce David Ruiz, in my opinion, a brilliant young mathematician from the University of Granada, Spain. David is a leader in the field of elliptic equation for his work that has been published in high-impact journals, and also for his collaborators who are central characters in this area, such as Andrea Macchiodi, Jean Van Schaffner, Antônio Brossetti, Giovanna Cerami, Antônio Soares, and Davi Arcoia. And in this seminar, David Ruiz presents work compactly supports solutions to the stationary 2D Euler equations with non-circular streamlines. David, you have around 14 minutes in order to do your presentation, please.
Okay, thank you, Giovanni, for the introduction and also for the invitation to this seminar. It's a pleasure to participate here. And all I'm going to talk about today is joint work with Alberto Enciso from ISEMAT in Madrid and Antonio Jesus Fernandez, who is also in Madrid, but in the Autónoma University. Okay, the outline of my talk is the following. First, I'm going to introduce the problem I'm interested in, which is as simple as this. I will be focused on steady solutions of 2D Euler equations which have compact support. This is the topic of my study here. And we will look for certain type of solutions to this problem, and we will do that via a semilinear elliptic equation. And in order to do that, I will use a local bifurcation argument, and that will be divided in 3 sections, and that are those 3. So let's get started. And so basically, the Euler equations model the behavior of a fluid which has no viscosity and no compressibility, and are as follows. These were found by Euler many years ago, centuries ago. And in this equation here, V is the velocity field and P is a scalar, which is the pressure. Okay, so this is the Euler equations. And I'm going to consider first steady solutions. Steady solutions mean that the velocity field V is not changing in time. So it's something that depends only on x, and in this case, the Vt derivative goes away, and then we obtain this system of equations. And moreover, even in this setting, we are interested in solutions which have compact support. What does it mean? Well, we are looking for a fluid in which the velocity field is 0 outside a compact region. So there, the fluid is quiet, it's not moving. And in a certain region, it starts moving, and the velocity field is constant at each point. Of course, this is possible because our model has no viscosity, so such a thing could be possible. So first, one could wonder if there are such solutions. And let's start with the 3D case in 3 dimensions. And actually, the existence or not of this type of solutions has been an open problem for many years. And there were some rigidity results telling you that under certain conditions, then you do not have such solutions, apart from 0, of course. But quite surprisingly, a solution has been found recently, and it was a paper by Gavrilov in 2019. And there is another extension of these arguments by Konstantin, La, and Vikol. So actually, we do have solutions in 3D in this form. And this is the solutions that Gavrilov has found is of a very specific type. It's a solution, a set of solutions in which the pressure is constant along the streamlines. So the streamlines are the trajectories of the fluid, and the pressure is constant on these lines. Okay, so this is regarding the 3D case, but in my talk here, I'm going to focus on the 2D case in 2 dimensions. And in 2 dimensions, actually, it is very well known that there are solutions of a steady Euler equations with compact support. And let me explain you how we can find them. Well, 2D is very special for me from many points of view. And one thing is that since the fluid is always in the plane, then the vorticity, which is the curl of the velocity field, it points upward. So it's two components are zero, and there you only have the vertical component, which is this one. And so you can identify it with a scalar. So the vorticity is a scalar, and then the first equation of the Euler equations turns out to be equivalent to this equation here. So that the gradient of the vorticity is orthogonal to the velocity field. Or in other words, along the streamlines, the vorticity is constant. Okay. That's the first thing. And second thing, another thing that you can do in 2D is the following, is that since you have also the second equation for Euler equations, which has the divergence to be equal to 0, and then because of that, you can define what is called the stream function. And this is a function such that the velocity field is actually the gradient perp of the stream function. So the stream function is a scalar function. So now we pass from vector PDEs in a scalar PDEs, and it's written in this form. And by definition, also psi is constant along the streamlines. So the vorticity and psi are constant on the streamlines, so their gradient point in the same direction. Okay. And moreover, if we take into account that V is the gradient pair of psi and the vorticity is the curl of V, then what we obtain is that the vorticity is the Laplacian of psi. So in the end, what you find is that if you want steady solutions of 2D Euler, what you have to do is to find a stream function psi satisfying this equation here. And this is all you have to, all you need. Okay. So basically, this implies that as I said before, that the gradient of psi and the gradient of the Laplacian of psi, which is the vorticity, are parallel. They point in the same direction. And this is the only thing. As long as you find a function psi satisfying this property, you have a solution of a steady 2D Euler equation. Okay. Okay, so now this is the equation that we have to consider, and that is a very easy way to find solutions of this equation, and is the following: you can take any psi which is radially symmetric, and the reason is that for any radially symmetric function psi, the gradient of psi points in the direction of x, but then the Laplacian of psi is also a radially symmetric function, and then it has the same behavior. So the gradient are parallel. Okay, so any radially symmetric function you can think of is a solution of 2D Euler. And in particular, you can take compactly supported functions, C infinity, compactly supported functions, which are radially symmetric. Okay, so you have, as you see, plenty of solutions with compact support. Okay, these solutions are radially symmetric, but you can build another thing. You can take a radially symmetric function, something like this, and then very far away, you can push another bump in the same way, which is also really symmetric with respect to another point. And this will be, again, a solution of 2D Euler with compact support. Those functions, we refer to these type of functions as locally radial. Okay. But in all those cases, the streamlines are circles, because the streamlines are just connected components of the level curves of the stream function. So in all cases, the particles move in circles. So the basic question I want to address here is if those solutions have to behave in this way, or in other words, if you have solutions where the streamlines are not circles. Okay, this is the question I want to study here. Well, regarding this question, there have been many results. I'm going to divide the results between rigidity results and flexibility results. So in rigidity, those are results in which they tell you that under certain conditions, then actually the streamlines are circular. Okay. And the first result I'm going to comment on is in the patch setting. A patch is a solution in which the vorticity is just the characteristic function of a certain domain. Okay. In this case, if the vorticity is the characteristic function of a certain domain, and the domain is C1, for instance, then if the solution, if the solution then has to be really symmetric, and this has been proved by Frankel if the domain is simply connected, but this condition has been dropped later by Gomez, Serrano, Park, Shi, and Yao. Okay, but this is in the patch setting. Also, yeah, well, in this case, the vorticity has compact support, but not the velocity field. Okay, so it's a little bit different from my perspective. And what about in the smooth setting, in the solutions that are smooth? Well, also in the same paper, Gomez, Serrano, Park, Shi, and Yao, they have proved that for any non-negative compactly supported solution, then omega must be locally real if omega is, it has compact support. So again, here is omega, which has compact support. Okay. And regarding the velocity field to have, if it has compact support, there is a result telling you that if the domain in which V is different from 0 is just an annular domain, something like an annulus, then it must be a round annulus and the streamlines are circular. And this is a result of myself in 2023. What about flexibility results? And well, there have been several results concerning weak solutions of 2D Euler. The first one I want to mention is the existence of L-infinity solutions that are not locally real. And this is a byproduct of our paper by Ciofruta and Sekeligidi, and in which they use convex integration. In a recent paper of mine, which has a different motivation, but as a byproduct, I can find also another solution, which is L-infinity, and a weak solution to 2D Euler with compact support. Okay, but this is for L-infinity solutions. The degree of regularity has been improved, first by a paper by Gomez, Serrano, Park, and Shi. And in that case, they work in, say, vortex patch setting. What they do is to find a linear combination of vortex patch setting, vortex patches. So this is a linear combination of characteristic functions on certain domains, and they prove that if you choose the parameters appropriately and the domains appropriately, you can have a solution which has compact support. Okay. But here, the solutions are continuous, but not C1. And the reason is that the vorticity is only L-infinity. It's not continuous. It's a sum of characteristic functions. Another example of a continuous, but not C1 solution, with which is not locally real for 2D Euler, has been given in collaboration with Enciso, Fernandez, and also Sigbaldi. And also here, the main motivation was different, was a question related by the well-known Schiffer conjecture, but I'm not going to talk about this in this talk. Okay, so basically, there are flexibility results, but they stop at continuity. And then they don't even arrive to C1, and so there are only weak solutions because the Euler equations are 1D partial differential. One of 1 degree PDEs. Okay. PDEs of first order. So the main result I want to report today is that we are able to construct CK solutions that are not locally real with compact support. And here K can be any given integral. Okay. So this is the result. Okay, so let me say something about the proof. The proof uses what is called a local bifurcation argument. So basically, you have a curve of trivial solutions that in my case, they're going to be radially symmetric solutions. They're not so trivial, but they're radially symmetric ones. And we want to see if we want to prove that there exists a bifurcation of non-radial solutions from this family. Okay. So the basic idea in general is the following. You have a nonlinear map F from a certain open set of a binary space X to Y, and that depends on a parameter, which is in an interval I. Okay, and this is a map which is C1. And imagine that you have a curve of zeros. For instance, f of t 0 is equal to 0, or f is equal to 0 in a curve. But here we put just 0 as the solution. Okay. So you want to find if, apart from this trivial solution, trivial family of solutions, you may obtain another one. Okay. So this is the picture that we have. So here in representing the parameter t, here is the space x of definition. In this horizontal line, we have a set of trivial solutions, and we want to find if there exists a bifurcation departing from some point t star. Okay, so if you have such a solution, such a branch of solutions, then necessarily the differential of the map f when t is equal to t star at 0 must be degenerate. And the reason is that if it were not degenerate, then the implicit function theorem will tell you that the only set of solutions are just a curve, but you already have a curve, which is the trivial one, so you would be over. So the existence of this branch is in contradiction with the implicit function theorem, and then this tells you that this operator has to be degenerate. Okay, but this is a necessary condition. What about sufficient conditions of our bifurcation? Well, there are several theorems, and we are going to use one of them in this talk. There are several theorems that tell you that you can do that, but in all of them, this operator, the differential operator of T star, needs to has finite dimensional kernel and co-kernel. So you have an operator that is degenerate, but the kernel is finite dimensional, and also the co-kernel is finite dimensional. And this is always required if you want to use usual I don't know, Kernel-Rabinowitz theorem or their local bifurcation theorems. And why I say so, and the reason is that this equation here that looks so simple, actually it's very degenerate. For any solution you can think of, you have an infinite dimensional kernel. And the reason is that every real symmetric function is a solution. So you have lots of degeneracies of the equation. So, this tells you that in a certain sense, this equation that looks so simple actually is not that simple. And maybe it would be better to try to find solutions to that equation by looking for a specific type of solutions. Okay. In order to reduce all those degeneracies that we have. Good. So what can be this specific type of solutions? Well, I thought about Gavrilo flows in which the pressure is constant along the streamlines. Maybe one could think that maybe one approach could be to try to do the same thing in dimension 2 and to look for solutions in this form. Okay, but it turns out that in dimension 2, Gavrilo flows are too rigid. Actually, if you want them to be compactly supported, then you only have locally radial things. So this is not good for us because we want to find solutions which are not locally radial. Okay, and this is a result by Sharafutdinov. There are other specific types of solutions that are vortex patches that I mentioned before, but vortex patches, as I said, the vorticity is a characteristic function, and then it is by definition it cannot be smooth. It is an L infinity function. So a good way to try to prove this is to look for semilinear elliptic equations. And why is that? Because if you have psi, a solution of a certain semilinear elliptic equation in this form, for any function f that you can think of, okay, then if you compute the gradient of Laplacian of psi, it turns out that this is minus f prime of psi gradient of psi, and this is parallel to the gradient of psi. So any solution of an autonomous semilinear elliptic equation in this form gives rise to a solution of 2D Euler. So, okay, so this would be an idea, but we have to face one first difficulty. The first one is the following. If we want a solution with compact support, then let's say phi equals 0, okay, then Laplacian of 0 is 0, so f of 0 needs to be 0. But then you have the 0 solution, and you have also your solution. So in a certain sense, you are contradicting the unique continuation of elliptic PDEs. And this is possible only if f is non-Lipschitz. If f is Lipschitz, you have unique continuation, and such a solution cannot exist. So first, you have a problem here, and this is that you have to look for a function f which is not Lipschitz regular. And this is also a problem in order to prove bifurcation, because for bifurcation, you have to differentiate. But if f is not Lipschitz, then the differential is going to be singular. And this is one of the difficulties of our work. That's the first thing. But the second thing is that, okay, we were trying to do that. And in the end, we came up with this result. This is another rigidity result of we gave, and also in the same work. By the way, all I mentioned here is, I'm mentioning here is in paper, is posted in the archive. And so this theorem tells you that if you have such a solution, M psi C3, then if the gradient of psi is completely supported, then psi is locally radially symmetric. So there is no hope to find a solution as we want, at least if you want C3 solutions or higher. Okay. So the idea here is to change a little bit and to look for solutions to similar elliptic equations with non-Lipschitz nonlinearity, which are going to be also non-autonomous. And this is one of the main new ideas in this work. So let me talk about this. So let's talk about the similar elliptic equation I'm interested in. So basically, the idea is the following. I'm going to focus on, I'd like to find a solution of this equation here, where f of x and psi is a certain nonlinearity, and it can be obtained by gluing together two different nonlinearities, and I'm going to call f minus and f plus. So the idea is that we glue together those two functions in such a way that close to any point, psi is a solution of either one of similar elliptic equation or the other. And of course, these two functions coincide in a certain region, and then you can do this gluing. And in this way, psi is a solution to the Euler locally, but to the Euler is local equation. So you would obtain a solution to the Euler. Okay. Okay. So this is the idea. Now let me mention how can we try to build this one parameter family of radial functions, of radial solutions. The idea is the following. The domain that I'm going to consider is an annulus with inner radius a minus 3 and bigger radius a plus 3. And a is going to be my parameter. I'm going to move the parameter. So we are working on annuli of width 6, and we move the radius from, we move the radius from 4 to plus infinity. Okay. And we want to find a certain solution psi sub a of a certain function f, which is, as I said, a gluing both functions. And we also need that psi goes to 0 very quickly at the boundary. And the reason is that we want a CK solution. But outside the domain, the solution is 0. So you have to match with it with k derivatives. So I'm going to look for solutions that behave like the distance to the boundaries at the boundary at power m. And n is going to be a big quantity. So this is the family of solutions. So here is a minus 3 and a plus 3. Basically, the construction is as follows. I first solve a very simple equation. For instance, minus Laplacian psi equals 1. And you obtain a solution. And then you truncate it on the boundary so that it becomes very flat on the boundary. Okay. This gives you a certain f minus here and a certain f plus here. But since the truncation has been given here and here, f plus and then minus is going to coincide, and they are going to be equals to 1 in the other parts. So basically, in this rectangle, the function is f minus. In this rectangle, the function is f plus. And in this rectangle, the function is exactly equal to 1. So yeah, so this is a solution that is locally autonomous, let's say. Well, of course, this is the real profile. But the good thing of this construction is that if you build a solution which is not radially symmetric, okay, to the same equation, then it's going to be also locally autonomous, and then it's going to be a solution of 2D Euler. And the reason is that you don't touch this white region. This white region is the only region in which you do see the variation in x on the function f. Okay. Okay. And now the function f minus, and f plus are depicted here. So as I told you from a certain point on, it is equal to 1, so they coincide, and they are not Lipschitz at 0, as I mentioned. If you want to have this behavior at the boundary, then f has to be non-Lipschitz at 0. Okay. So now, what is the idea here? Well, I have my annuli, which is annuli of inner radius a minus 3 and a plus 3, and we want to perturb the boundaries of the domains. And the perturbation of the boundaries are going to be given by the small function, by the small b and capital B. And those domains are going to be omega a, b, capital B. Okay, domains like depicted here. So the idea is that for certain a, we do have small functions, small b and capital B, such that you have a solution there as we want. And this is the statement of the theorem, of our theorem, in its elliptic version. Okay. So the idea is that there exists a certain a star, and such that we have an, bn, and capital Bn, and solutions in the corresponding domains. Moreover, the solutions behave like the distance to the boundary of power m, so they match ck, certain k, up to the boundary, and they are regular inside, so they are regular. Okay, so this is the theorem. So the solution for 2D Euler depends on this elliptic version of the theorem. Okay, so as I said, we are going to apply a nonlinear local bifurcation argument, so we have to define a nonlinear operator. And I said I'm going to use the parameter a as a domain, and I'm going to perturb the boundaries, but in practice, you cannot do that because you need a fixed Banach space in which you can perform the perturbation argument. So you have to pass to a fixed domain via a diffeomorphism, and this is what we do next. So we fix an annulus. This is an annulus of radius, inner radius 1 and outer radius 7, for instance. Okay. Rho is the distance to the boundary, which is going to measure how far are you from the boundary, and this is going to be used later. And we pass all our problem in omega a, small b, capital B, to this omega. Okay. So we use a diffeomorphism, which I'm going to call it phi, and I pass via this diffeomorphism to an equation in omega. And the equation is just this. This is the Laplacian operator, and this is the composition with the nonlinearity. Okay. Of course, as I mentioned, we need to ensure also that the solutions behave like rho to the power m at the boundary. And let me call psi a was the family of solutions, or 1D solutions that I mentioned before, and I call psi a tilde when I pull them back to the domain omega, and when you don't have any boundary deformations. Okay. So the nonlinear operator is written in this form, so it's a little bit complicated. You don't need to look at the exact computations, but just several ideas. Well, forget about this factor. This is a factor which is written here for convenience. So basically, this is the Laplacian operator via the diffeomorphism, and this is a nonlinear operator. This is the final certain function w. And here I have the boundary deformations, small b and capital B, and they depend on W. Actually, they are the boundary values of W up to a certain constant, which are not important for us. Okay. So W in its boundary values encodes the variations of the boundaries. Okay. And then we have psi a tilde, which is the pullback of our 1D solution, or radial symmetric solution, and then the variation of psi tilde, which is this fact, this term here. This is rho to power n minus 1. Rho is the distance to the boundary, as I said, and theta w is a suitable correction. It has a complicated form, but it's just a suitable correction such that it is 0 on the boundary. W is not zero at the boundary, not necessarily. The value of the boundary are the modifications of the changes on the domain. But then we correct it to make it zero at the boundary, and this is the function. Okay, so this function here that I will call U would be a solution to the problem when you go back to your original domain via the diffeomorphism. Okay. Okay, so this is the nonlinear operator. Where is it defined? Well, the functional setting here is a little bit tricky. I'm going to be very quick here. First, the domain of definition is going to be called xj. Xj is the functions that are in the Sobolev space Hj, such that this function is also in Hj. So basically, what this tells you is that you can compute j derivatives on W, and you can also compute j+1 derivatives on W as long as at least one of the derivatives is with respect to R, and if you multiply it by rho, then this belongs to L2. Okay, so this is the idea of this space. And the norm is the natural norm for this space. Okay, so the domain of my nonlinear operator is going to be a small neighborhood of 0 in this new space. And the codomain is also tricky, and is given by the sum as Banach spaces of these two spaces. So again, here we have anisotropic spaces. Here you can compute j-1 derivatives for the right summand, and for the left one, you can compute j-2 derivatives, and you can compute j-1 derivative only if you are computing derivatives at least one with respect to R. But for those functions, you impose them to be equal to 0 on the boundary. So this is a combination of the two. Well, it turns out that our nonlinear map maps Oj, which is in Xj, into Yj. So this function setting seems to work. Okay. You may wonder why we would choose these anisotropic spaces. And the reason is that, let me mention a previous paper by Formin, Len, and Weth. They were trying to do something which is different but related. It would be related to this case when m equals 2. And they found out that if you try to address the problem directly or with a more direct method, then you have a problem which is called of loss of derivatives. But by posing this problem in anisotropic Holder spaces, they were able to overcome this difficulty. So what we have done is to take this setting of them and to adapt them to the Sobolev case. And we need to use Sobolev spaces because in what follows, I'm going to mention right now, the linearized operator is going to be singular, and to deal with it, we need to go to Sobolev. Okay, so let's go to the linearized operator. So when this map that I mentioned before is of class C1, this can be proved, and the derivative is, well, apart from the usual factor, is just the usual derivative. So basically, this is the Laplacian with the pullback operator, and this is f prime. But f, as I told you, is not Lipschitz, so this gives rise to something which is singular. Actually, what you have here is something that behaves like a constant times over rho squared, where rho is the distance to the boundary. Okay. So basically, you can decompose the derivative of g in A at 0 as two summands. This Ta, which is this operator, and this is the main part of the operator. So this operator is basically the Laplacian minus a constant times rho squared. And then there is another operator Ka, which is the remainder terms. Okay. This operator is critically singular because this rho squared in the bottom. So it has the same degree of homogeneity of the Laplacian. So the key result here is that this operator Ta is an isomorphism from Xj to Yj. And this is what was important for us. Okay. And moreover, the remainder is a compact operator. So in particular, this differential is a Fredholm operator of index 0, and this is very good. This is very convenient for doing local bifurcation. Let me mention a couple of words regarding the proof of this. to prove this result, we have to develop a regularity theory for this kind of operators. So this is the operator I mentioned before, and on the right-hand side, you have an element which is in yj, up to the usual factor that I mentioned before. And in order to do that, we have to, the way that we did it is to use a Fourier decomposition. And for using Fourier decomposition and that everything goes well, we needed a Sobolev framework, okay? And so we did a Fourier decomposition and then Frobenius theory to study the resulting singular ODEs. Let me mention that after our paper appeared, and from a completely different point of view, also Rosoton and Restrepo were involved in looking for this kind of operators, and they were able to give a regularity theory in Holder spaces, but not anisotropic. We are interested in anisotropic whole spaces. Maybe combining this result by Rosoton and Restrepo in the anisotropic setting, we could do everything without using Sobolev minorities with the map. Okay, so now we go to the bifurcation argument. And the theorem that we are going to use is the theorem that is called usually the Krasnodębski theorem, which is based on the erasure of the degree. So basically, you have a map, as I mentioned before, such that you have a trivial family of solutions. Okay, in our case, this is the one parameter family of solutions of real symmetric solutions that I explained to you before. You need that the map is identity minus compact, and this is important. Okay, and also you need that you have 2 points on the interval such that the differential on those 2 points is non-degenerate, and they have indices with different parity. And here I call the index the sum of the algebraic multiplicities of all eigenvalues which are negative. Okay, so if they have different parity, then they can it can be proved that in between you have a bifurcation point. So in order to prove such a thing, in order to apply this theorem, well, first we have to reformulate the problem in a different setting, because we need here an operator which is identity minus compact, and our operator is not exactly in this form, but it can be rewritten. And second, we are going to take A sufficiently large. So I told you A is the distance of the annulus to the origin, so I'm going to take very large annulus. Okay. And the reason is that in this way, I know very well the behavior of the functions and everything, because everything looks like an ODE when A goes to plus infinity. And also, we're going to we need to make use of symmetry. Actually, we're going to make use of a symmetry, what is called the Edric symmetry. So the symmetry of the functions that are symmetric under the symmetry group of the L-sided polygon. Okay. So in general, there exists a sequence of eigenvalues of the linearized operator with finite multiplicity. This can be proved, and that they go to plus infinity. And so we can analyze these eigenvalues, and we can choose A and also L. Let me remind you, L is the degree of symmetry. So, okay, so the number of rotations that you can have symmetry. And there exists L sufficiently large and A0 and A1, which are also large, such that the following holds. So first, the first eigenvalue and the second eigenvalue, both of them are related to radial eigenfunctions, and they are both negative. Okay. Instead, the third one is not related to a radial eigenfunction, and it can change, and actually changes from negative to positive. So in A0 is positive, and in A1 is negative. And this is good, because in this way we have a crossing of eigenvalues, right? And we can also prove that when it becomes 0, then it is simple. So when you pass from positive to negative, there are only one dimension less. The index increases by 1. So the indices on the left and on the right have different parity, and we can apply Krasnodębski theorem and obtain a local bifurcation of solutions. And that's all. I thank you for your attention.
Congratulations, David, for this very nice talk. and for your
Thank you.
presentation. Is there any question to David
There are messages.
or comments?
There are messages in the chat. So how do you ensure that the perturbation is a compact operator? Well, the basis is that, as I told you, the differential operator is an isomorphism plus a compact operator. And in this way, you can rewrite your problem such that it is identity minus compact. This is not immediate, but it can be done. Basically, since you can use the isomorphism part to invert everything, and then you can rewrite everything as identity minus compact operator. And then Mateus is asking, in complex surfaces without boundary, smooth functions, always, of course. Are there similar studies in this situation, for instance, in this sphere? No, I don't know anything about that. Well, of course, they have compact support. There are solutions, of course, in these settings, but so what you mean is solutions that have a support, say, yeah, in simply connected subdomain or something like this. No, there is nothing like that, as far as you know. Well, in the torus would be easy because you take our function and then you extend it periodically with a large period, and this could be okay. But for the sphere, for instance, I don't know.
David, there are other questions in the chat.
Yeah, so Luis is asking, how was the definition of the anisotropic space? Okay, so let's come back to this. So these are the definition of the anisotropic space. So xj is a function w, which is in the Sobolev space, such that the derivative with respect to r is the real variable, and theta is the angular variable. The derivative with respect to r is also in hj. So basically, this tells you that you can compute j derivatives always, and you can compute j plus one derivative, but at least one of the derivatives has to be with respect to r. And if you multiply it by rho, then it is in R2. Otherwise, you don't know. Okay. And this is the domain. And for the codomain, it is this space. So this is the sum of these two. This is isotropic, but this one is anisotropic. So.
Any question?
Oana is asking a similar result expected in the setting of non-stationary solutions. That's a very good question. I don't know. I'm not sure what you mean by that. Here we are looking for classical solutions. So solutions, I mean, could not depart from zero and then move and then become to zero again as the usual weak solutions for 2D Euler. So maybe solutions that move in time, like, yeah, could be, for instance, if you look for rotating solutions, this could be a thing to think about, yes.
Thank you, Luis, Mateus, Joanna, for the questions.
Thank you.
And more question?
I have a question.
Yeah, Diego.
Can you obtain a say infinity solution?
Well, that's let's say not yet. In this case, we have CK for any given K.
Yeah.
So C infinity is something that we are thinking about.
Okay.
But then the main difficulty is that, as you saw, you have to cut the function to zero, and you want to be like rho to the power m. So if you want C infinity, you would need an exponential there.
Yeah.
And if you put the exponential, then the linearized operator becomes supercritical, not only critical, but supercritical. And then the things are more complicated. So the the linearized operator have something over rho squared, then you would have something like rho squared log of rho or something like that.
Okay, thank you.
So
And I have another question is about the stability.
well, this solution is should be highly unstable.
Yeah. Okay.
Actually, stability solutions for L2, I mean, stable L2 solutions into the Euler, steady, for instance, is not so clear to me. I mean, it's not so clear if there are any stable solution in this fashion. Because if you try to apply, for instance, Arnold setting, it never works. But it doesn't mean instability, right? So the Arnold hypotheses do not work, do not hold.
Okay. Thank you very much. Very nice talk.
Thank you, Diego, for your question. Any question? So, thank you, David, for your availability to participate to our seminar. And today